This video is about types of reactions. The whole idea here is reactions fall into patterns. And the ones I'm going to show you are the most common patterns. It isn't exclusive, but these are very common patterns. What we're leading to eventually, in fact in the very next video, is you predicting products. That is, looking at reactants and deciding what the products are going to be. But first, let's just see the patterns. So the first one we're going to talk about is called synthesis. Synthesis is a perfectly good English word. It means to make something. So that's what synthesis is. It's two reactants coming together to form one reactant. Very often it's two elements coming together to form a compound. So a synthesis reaction might be hydrogen gas plus oxygen gas becoming water. Okay? That is a synthesis reaction. You will notice it is not balanced. I did not try to balance by putting the reactants together into a product. I just knew this is what those two things made. If we wanted to balance it, we would say, oh, 2 oxygens here, only 1 oxygen there, there's 2, that gives me 4 hydrogens, 2 there. That is a synthesis reaction. Now the opposite of a synthesis reaction is a decomposition reaction. Decomposition means falling apart. So a decomposition is the opposite of a synthesis. H2O goes to H2 plus O2. 2 there, 2 there. The opposite of the reaction I just drew. Just to tell you, by the way, not every decomposition goes to elements. One very common one is hydrogen peroxide. That's the stuff you put on your cuts that bubbles. When that decomposes, it decomposes to water and oxygen. Now let's see, there's 3 O's there, only 2 O's there, so a 2 there and a 2 there. 4 hydrogens, 4 hydrogens, 4 oxygens. That is balanced. Okay? But you'll notice this is a decomposition reaction, but my products are not elements. So they don't have to be. It's just something falling apart into simpler things. Another very common reaction is H2CO3. You may recognize that as carbonic acid. That's actually a very unstable thing. It falls apart into water and carbon dioxide gas. That's a very common decomposition reaction. The next one we're going to talk about is a cationic single replacement. There are actually 2 kinds of single replacements, cationic and anionic. We'll get to anionic in a second. Both of these follow a single replacement pattern. Remember, a cation is a positive ion. So a cationic single replacement is one where you have some sort of metal, because remember, metals are the ones that want to make cations. This is not a cation, by the way. This is neutral. There's no charge written here. That's a metal plus some kind of compound. I'm going to call it M prime, meaning a different metal, and X, some kind of anion. Okay, so I have a compound that's made of a metal, which is different from this metal, and some sort of anion. Nobody here has charges. Remember, things I have out in the world do not have charges. What happens is this guy comes in and replaces that guy. So we end up with Mx plus M prime. There's been a transfer of electrons here. This guy's neutral. Now he's a cation bonded to this anion. This guy was a cation, and now he is a neutral species. Okay, there's been a transfer of electrons here. This is something called a redox reaction, which we'll get to later. Let me give you an example of this. Lithium plus sodium hydroxide goes to lithium hydroxide plus sodium. The lithium has come in and replaced the sodium. Now notice how I've done this. This guy's a metal. A metal always makes a cation. It's always going to replace the other metal. Please don't put the two metals together into some sort of compound, because that's not going to happen. Two positives are never going to come together. It's got to be a positive and a negative. The metal has to replace the metal. Don't throw it out here and make it NaLi or something. Don't do that. You know what compounds look like. That's why we spend all that time on naming. So that is a cationic single replacement. What do you suppose an anionic single replacement is? It's some sort of non-metal. This is a non-metal, which of course wants to make an anion, a negative ion, plus, again, some sort of compound. Okay, a metal and an anion. Again, neutral, no charge here. Obviously no charge here. These two cancel each other out. That's the whole point of a compound, right? And of course, what I'm going to get as products is M bonded to Y. You'll notice the positive guy's always first when I write these things. Don't put YM, MY, plus X. Again, there's a transfer of electrons here. This Y being neutral becomes an anion. This X, which is an anion, becomes neutral. So these are very common with halogens. Remember halogens, group 17? Very common with halogens. So I might say something like F2. Remember, halogens are the ones that are sub 2s when they're by themselves. But it's still a single element. Plus FeCl3 goes to FeF3, iron 3 fluoride, plus Cl2. Okay? Again, I have to balance this guy. That's okay. Just because that guy's a 2 there does not mean it has to be a 2 there. Just balance. 3 there, 2 there, 2 there, 3 there. 6 Fs, 6 Fs, 2 Fes, 2 Fes, 6 Cls, 6 Cls. Notice I'm still using the same naming rules, the same writing formula rules I knew in the last chapter. This guy's a plus 3 on this side. This is a plus 3 here. This guy is not changing charges. The F is going from neutral to a minus 1, so I need 3 of them. The Cl is going from a minus 1 to neutral. Again, it's diatomic, but that is the correct formula. Double replacement. Double replacement is just what it sounds like. You've got 2 compounds and they switch. The analogy here is you've got 2 couples dancing. They switch partners. They have to switch partners, though, in an appropriate way. That is, the metal has to go with the non-metal. You can't have 2 metals together. You can't have 2 non-metals together. So, this would be something along the lines of HCl plus NaOH going to water, which is really HOH. This guy has bonded with this guy, plus this guy going with that guy, NaCl. And I have a double replacement. H has gone with the OH, Na has gone with the NaCl, Na has gone with the Cl. Water plus Na plus salt. You'll notice I didn't have to worry about any balancing here. This is all pluses and minus 1s, but I could. What if I have Ba3PO4 2 plus K2CO3? Well, let's see. The barium goes with the carbonate. Barium, I know, is always a +2. Carbonate, I know, is a -2. So that's just BaCO3. Don't keep this sub 3 just because there's a sub 3 there. You don't want to do that. You want to write the neutral species. Plus potassium plus phosphate. Phosphate, I know, is a -3. K is a +1. That's K3PO4. So that's 3 bariums here. That's 3 carbonates. So there's 3 carbonates there. That's 6 potassiums. Now I have 6 potassiums. Oh, and 2 phosphates. Look, I'm balanced. Ha! Okay, double replacement. 2 compounds to 2 compounds. Last one is combustion. For some reason, this is really hard for people, and I don't know why. Because the products are always the same. It's a very simple pattern. C with some sort of subscript, H with some sort of subscript. Once in a while you'll see an O with some sort of subscript, but for the most part, no. Plus O2 goes to CO2 plus H2O. That's it. Period. End of sentence. C something, H something, plus O2 goes to CO2 and water. That's it. That's a combustion reaction. And of course it needs to be balanced. So if I have something like C3H8 plus O2 goes to CO2 plus H2O. That's a 3 there and a 4 there. That gives me 6 and 4, 10 oxygens, 5. And balanced. That is a combustion reaction. Okay? Let's review. Synthesis. 2 small things become something bigger. Decomposition. 1 thing becomes 2 smaller things. Cationic single. A metal and a compound becomes a metal and a compound. Anionic single replacement. Non-metal plus a compound becomes a non-metal plus a compound. Double replacement. 2 compounds become 2 compounds. Combustion. A hydrocarbon, that is something made of hydrogens and carbons, plus oxygen goes to CO2 plus H2O. That's it.